Okay, hello again, everybody. So yes, as Helen said, Courtney couldn't be with us today. She had very bad reasons to stay back in Brisbane, so it's a shame for me because I have to give another presentation. Could be pity for you because you're stuck with me for the next 25 minutes, so let's see how it goes. And let's sort out attribution of authorship, so whatever you like about presentation, particularly about mineralogy, feel free to credit Courtney. And whatever you don't like about presentation of geochemistry, blame it on me. So let's move on. Am I in? Did I speak up? Okay, good. Fine. So just quickly take you through work GSQ did over the past couple of years on IOCGs, which was a fair bit. We'll talk about geochemical signature or other signatures of, and talk about different classes, geochemical classes of deposits, which we can recognize in the Cloncurry district. We'll talk about mineralogical signatures, largely based on spectral mineralogy. So we do have access to TIMA data, which will speak about what we can see in spectral mineralogy. And we'll take you through in more detail deposit footprints based on a case study on Ernest Henry. And a necessary warning, borrowing from Mark Twain. So I have a lot of slides, so I'll have to speak a bit faster than I usually would. So we have a pretty good coverage of the region. So we covered 18 deposits of their camps, with just a few exceptions of noticeable and worth discussing IOCGs. So we did high-log scanning of more than 12 kilometers of continuous core plus individual samples, and multi-element geochemistry consistently done for more than 1,000 samples. And just quickly flip through the examples of sample distribution. So that's samples from Elliott Swan, multiple boreholes, multiple samples from boreholes going through ore body and as far away as we can get. Similar for LOEs, about 100 samples from very shallow, from very deep, going through different lenses. So we have a pretty good coverage. Rosby corridor for a whole series of individual deposits. It's difficult to show them all in 3D. Most samples we're going to discuss about Little Liver, and we still don't have results for a bunch of others. So it's still in the lab. So on geochemistry, we have samples from 43 drill holes dating back to the historic study of Uncover Cloncurry CSRO. GSQ funded study, which was delivered in 2015. We sampled another 48 drill cores, new samples ourselves, and done together with our collaborative partners, CSRO and cohorts. And overall, as I said, about 1,000 samples consistently done for acid digestion, lithium borate fusion, fire assays, 67 elements, pretty much everything which matters in IOCGs, plus many more. And more than 200 samples have serious copper grades. So we do have a good coverage of ore samples and alteration and background samples as well. So let's see what we found in geochemistry so far. So very easy exercise, beautiful, simple to use IOCG alteration index done by good people from South Australia. Let's have a look how Cloncurry IOCG deposits stack up on this IOCG alteration index for Golocraton. And it doesn't look too great. Mind you that these samples are all mineralized 0.2% copper or more. So by the look of it, so if we draw a line at 0.5, so something like 50-50 chance of being like Golocraton IOCGs, just two deposits in the entire Cloncurry district would make the cuts, which is Ernest Henry and E1. And everything else would make pretty sad Golocraton style IOCGs, clearly indicating that there are different geochemical signatures, and the vast majority of IOCGs in Cloncurry district are anything but like Olympic Dam. So just quickly going through the joy of statistics. To quickly summarize, all of the IOCGs have a common signature in copper, gold, silver to various degrees, sulfur, tellurium, selenium. So that's where the commonalities end, and everything else is more or less different. Only some deposits, very few actually, have also enrichment in uranium, light rare earths, tungsten, moly. And that would make the bulk of signature of gold-craton IOCGs, as well as arsenic, antimony, fluorine.
Your microphone is, can you just adjust?
Yes.
I'm going to try to adjust it so that it's actually pointing at your mouth rather than, because it sort of sounds like you're talking in a garbage can.
Thank you.
Sorry, everyone.
Yeah, I'm struggling.
Yeah. I know this isn't COVID safe. That's a mistake.
Let's try. I'll just stay very still. Okay, good.
Or talk louder. You could just talk louder.
I will try. How about that? Everybody can hear me? Good, good. Fine. So the main conclusion of this busy slide, and it's all the slide, but it's easier to see, that there is a fair bit of variation within the overall IOCG signature between individual deposits. And to see it a bit better, a little bit more of a machine learning exercise, just a simple discrimination projection exercise, trying to distinguish different signatures of ore. And there are 3 distinct clusters which don't overlap, and probably one of them can be split further. So one of them is typical to just 2 deposits completely, Ernest Henry and E1, and just a few examples now and then in other deposits. Another one is by far the dominant cluster shown here in green. That's pretty much the bulk of deposits. Close to this second cluster in green is a cluster of mostly 2 deposits, Barbara and a good half of samples from Eloise, but they somewhat stand apart. And pretty strange and pretty poorly understood group of analysis from Caltha, and also some analysis from Osborne, Star, and Great Australia. But for now, it's just a bit of a machine magic. Let's just try to put some geochemistry on top of that. So I showed this diagram before, just to indicate that what distinguishes Ernest Henry and E1, and what makes it classical IOCG signature is that polymetallic signature with molybdenum, tungsten, arsenic, antimony, fluorine, barium. But that signature is very typical just for Ernest Henry and E1. Some others, like Swan, is characterized by enrichment in light rare earths. The blue cluster of Caltha has not very significant, not major, but quite consistent enrichment in heavy rare earths. And well, what typifies the orange cluster is not quite clear. So very quick attempt to identify signatures group by group. Class 1 is what everybody knows as the IOCG signature. Second one is missing on the polymetallics and most of moly, tungsten, and fluorine, barium. What makes class 3 stand out, we're still not quite sure, but quite often these deposits have high silver and locally zinc, but also cobalt and nickel, which is not that common elsewhere. And the fourth one is characterized by indium and heavy rare earths. Let's have a look at mineralogy from spectral mineralogy. It's more than 12 kilometers of continuous core scanning, 37 drill holes distributed throughout its region, and subsamples, individual samples from 31 boreholes scanned by hull auger, so it's a pretty good coverage. And mineralogical data is collected on a centimeter scale. It's aggregated for presentation, but we have a pretty good handle on centimeter scale alteration and zonation. So overall, there is a great variety within deposits and between deposits, but all of them can be combined into 2 different broad classes. at a very basic level, one of them is characterized by lots of K-SPA and the other without. There are some other subdivisions, which is not quite clear if these subgroups belong in a larger group or separate, because, well, for example, in the first one, there is K-SPA everywhere, but the second group is characterized by much higher contents of carbonates. And some of these deposits are essentially the carbonate veins. And in class 2, which includes lots of carbonate veins, but also other deposits which are more like disseminated. There is also a group characterized by biotite and tourmaline. So it doesn't stand out in itself, but it also coincides with the geochemical group of Eloise and Barbara. Everybody likes to look at rocks more than looking at diagrams. So that's what class 1 looks like. It's a typical red rock alteration, mostly, but not always. Some of these K-SPAs, they look remarkably boringly gray. And this is typical for class 2. That's quite often described as a dark rock alteration. In some places, some of these rocks are distinctly green because of the presence of actinolite. And as you can see, Ernest Henry also has examples of this type of mineralization assemblage as well. And a quick attempt to put mineralogy and geochemistry together, including description of deposit form. I'm not going to dwell too much on that. The key message here is that there are good one-to-one relationships for some geochemical classes and mineralogical, particularly clear for Ernest Henry and E1. Very distinct combination of proximal alteration assemblage in geochemistry, and a little bit of variation with other groups. And here I used a shorthand version to describe geochemical signature. Well, there is no need to repeat that copper mineralization is anomalous in copper. So here just listing the elements which makes this particular class stand out from others. But in more detail, so in gross sense, it works fine. We can identify mineralogical and geochemical groups in the ICG family, but there are complications, particularly within larger deposits. In larger deposits of the scale of Ernest Henry or Swan, you can find examples of just about every mineralogical type and every geochemical type, with some exceptions. So it would be interesting to have a look in detail at individual deposits of major significance and its footprint. And we'll take you through an example of Ernest Henry, where we have done a fair bit more extensive study. So it's overall, it's 18 borehole samples sampled throughout the region, going far into what appears to be background, kilometers away. Overall, collected about 460 samples from 11 drill cores. All the samples were scanned by high logger, so we have a good control of the mineralogy, and more than half of them, well, about half of them, were done by multi-element geochemistry. So put it in a 3D context, and to indicate the scale of the spatial coverage, it's more than 4.5 kilometers north to south. And a fair bit of density of samples within boreholes, so we are reasonably sure that we do have enough coverage to speak relatively confidently about overall patterns of footprints within the camp. So the most typical, the most commonly described, the most commonly recognizable signal mineral of alteration in Ernest Henry is feldspar. K-SPAs in particular, and the traditional pregenetic studies depict a pretty easy, nice story. So it's early sodic alteration, later potassic alteration, both related to feldspars, L-bite versus K-feldspar. And in reality, it's a little bit more complicated. So first of all, there are at least 2, sometimes 3 different generations of every K-SPA. And some L-bite alteration looks remarkably red rock-like because of hematite dusting, and some K-SPA alteration looks very much like L-bite because some of the feldspars look very gray. So it will be useful to have a look if we can use multi-element geochemistry, as quite often used for acid digest geochemistry with good sodium and potassium. Let's have a look at if we recognize potassic and sodium alteration geochemically. So a quick and rough and ready geochemical discrimination diagram, where most samples can be classified as either potassically altered, sodically altered, or somewhere in between, including background. To put it more into geochemical context, or with typical polymetallic signatures characterized overwhelmingly by potassic alteration. Potassic feldspar alteration as interpreted from multi-element geochemistry. And a different view of the same data, also painting on this diagram distance to the ore shell. It's a bit complicated. But the main message here is that again, the majority of samples within the ore body and proximal to it are characterized by K-spar alteration. Distal from the ore body, that's pretty much everything on the right of the image. It's typically sodic alteration, and there are a few interesting anomalies, like some samples which are within the ore body very close to it. Are marked as unaltered or moderately altered, which deserves a second look. But first, let's have a look how distributed in 3D, which is a pretty interesting picture identifying inner zone of K-spar alteration. That's pretty much the ore body and very proximal. Distal zones characterized by sodic alteration. Well, so far so good. It's supposed to be original sodic alteration event, but there are some logically strange things. For example, very proximal to the Ernest Henry ore body, there is a whole bunch of samples which are marked as background, but at the same time, they do have a pretty distinct signature, polymetallic signature, similar to Ernest Henry ore body. So how does that work? How does that work? That we can see in multi-element geochemistry, polymetallic signature of the ore body, and yet the sample is characterized as unaltered. And that's what the sample looks like, and it's not very unaltered. In fact, it's a sample with chalcopyrite. So it's obviously it's a clear illustration of the fact that using a simple feldspar discrimination diagram from bulk geochemistry does not do justice to describe alteration story. And here are several images typifying so-called background or moderately altered rocks. And you don't need to use anything but your eyes to see that they're not particularly unaltered rocks. So they're quite obviously very seriously affected by hydrothermal alteration. So that's where mineralogy, continuous spectral mineralogy comes into play. Here we can distinguish both gross scale zonation going from the ore body into distal parts. And then we'll have a look at much finer detail, what happens within the ore body and proximal alteration. So here the big story is what happens at a kilometer scale, from distal 4 kilometers to the north, closer to ore. The first image is shortwave infrared, and the basic message is here. As you go from distal closer to the ore body, chloride abundance seriously declines. Abundance of amphiboles, mostly hornblende, declines, but at the same time increases concentration of actinolite, and clearly carbonates pick up at proximity. And another view from thermal infrared. Here we can see that L-bite is the dominant spectrally active mineral in distal settings. L-bite is gradually getting replaced and overprinted by biotite and replaced by K-spar towards the ore body. And another curious feature which we only recognized using the spectral data. There are actually two different K-spars, and they have a consistent relationship with copper mineralization. Microcline is typical for proximal alteration, but within the ore body, it's much more autoclized than microcline. So it's something new which we didn't know until we had a closer look at spectral data. So to make it easier to see in 3D, the same story. Distal samples are characterized by dominant, almost universal signature of hornblende, biotite, chloride, and albite. In intermediate settings, about 2-3 kilometers away, biotite, magnetite become much more prominent, with chloride as a matter of course and quite common, and K-spar appearing occasionally, but it's more like on centimeter scale veins. And within a kilometer or so from the ore body, it's dominantly K-spar, magnetite, carbonates with biotite and chloride. So let's have a look what happens in closer detail within that 1 kilometer. So can we see the difference between very, very proximal tens of meters of ore and more distal kilometer away? So here we can see that proximal alteration a kilometer away without much sulfides is typically characterized by microcline, lots of it. It's pretty much semi-pervasive, is seen throughout the rock. And that's why it's very difficult to recognize by looking at the core. So we have to check with Courtney a couple of times because these rocks don't look like red rock alteration. It's gray, dark gray rock. Closer to the ore body, that's a very curious appearance of quite clearly visible actinolite, which is present both proximal and underneath the ore body. And within the ore body itself, it's the part of autoclase, but there is a fair bit of microcline hanging around, mostly in the clasts, and apatite, calcite, and plenty of sulfides. Now let's go back and have a closer look at geochemistry, what we can see changing geochemically from the ore body to proximal alteration, and try and cross-validate geochemistry and mineralogy together. So geochemically, well, because if you remember the previous diagram of this kind where plenty of proximal samples were marked as unaltered sodium versus potassium, this is an attempt to interrogate geochemistry to try and define multi-element geochemical classes, the entire geochemical spectrum, not just sodium or potassium. And here, picture is much clearer. Pretty much everything within the ore body, everything with a clear multi-element geochemical signature of copper ore is characterized by ore cluster. A little bit more difficult to interpret cluster with less significant but still the same, just less significant polymetallic signature. It's quite typical for samples with carbonate actinolite plus or minus apatite assemblage with chalcopyrite and sodic alteration. And the spatial distribution of these different geochemical clusters. The picture is pretty solid. We're confirming multi-element geochemical signature within the ore body. There is a very interesting appearance of a geochemical cluster in purple, which only appears within 1 kilometer from the body and nowhere else, and that's what the rock looks like. That's the signal of potassic alteration with veining but without sulfides. And closer to the ore body and also occasionally as individual veins elsewhere, we can see this typical combination of chalcopyrite in carbonate actinolite veins, which is quite common in distal parts and more regionally. So I'll start closing up. So we have acquired consistent geochemical mineralogical data sets throughout the Cloncurry district. We have some deposits covered quite well, and that's courtesy of the companies who allowed us to collect that information. Glencore in particular for Ernest Henry, and Chinova for Swan. That's something which we're going to discuss in the near future. We have enough information to clearly say that there is a distinct mineralogical and geochemical signature, or rather signatures, and there are distinctions between deposits. And whatever is considered as a classical IOCG signature in Gola Craton and quite often quoted elsewhere In this region, it's only typical for Ernest Henry and E1. And all others are characterized by much simpler geochemistry generally, and quite often they're characterized by the absence of proximal case pair alteration. Identifiable footprints without going into any magic of mineral chemistry can be recognized within 1, sometimes 2 kilometers away from some ore bodies like Ernest Henry. And even though we have done a fair bit of work, we're still in the final stages of the project. So we're still going to do some more geochemistry and mineralogical work. So it's a final call for some more samples which were not covered. Well, Rocklands was a great emission. There are a series of small deposits. We're going to finalize geochemistry on Eva. We have good collection of samples, but data is not yet available. So if anybody in the audience has an interest to support more work in the next 3 months, well, here is your chance. We're certainly interested. And acknowledgments of our collaborators. So this work started as an offshoot of our work with CSRO from previous project. We're working closely with Codes for focusing their efforts on mineral chemistry, and there is every possibility to expect that with mineral chemistry we should be able to recognize distal signals more than 1 to 2 kilometers away, and there are some early results to suggest that this is indeed possible. John Huntington, we used a great deal to help us with special data interpretation, and CSRO Minerals were working with them very closely for the past 6 years on and off, and I hope this ongoing collaboration will continue. And of course, all the companies which allowed us to do all this work on the core and samples, without whose support it would not be possible. So with that, thank you.
Oh, there's lots of questions for Vlad.
Good.
Derek's on the way with the microphone.
Hi, thanks. When you get out to the 1 to 2 kilometre from it, have you thought about how you level the data sets for host rock types, given that as you head out there, the fluid tends to be rock buffered?
Yep.
So how did you go in the different PCAs when you actually leveled them against different rock types?
Okay, for now, all we did is, well, the good thing within 1 kilometer from, say, Ernest Henry, it's dominantly felsic to intermediate lithology, so most of the lithological change happens at further distance. So we do recognize that as we move from felsic to mafic hosts, the signature changes, but it's mostly mineralogical, not geochemical signature. So mineralogically, yes, we see plenty of hornblende in distal settings, and it has nothing to do with alteration. It's just when the mafic rocks. Geochemically, the geochemical signature is so dominated by these chalcophile elements that as long as we can see that, our host rock doesn't come into play.
A question from Johan.
Okay, thanks, Vlad. I think that's fantastic data set, and probably there can be done some more digging into that data set. It's so large. So first question was similar to what Nick was asking, but so my question now is, have you seen a depletion in magnetite as you go into the ore zone in Ernest Henry?
Okay, that's going into further detail into data. So pre-genetically, on the one hand, the most important host rock is magnetite hosting breccia, and there is a general correspondence between increased magnetite and proximity to ore. And in more detail, chalcopyrite is pre-genetically later than ore. So normally, the more copper you have, the less iron you have. But still, even the richest ore still has lots of magnetite.
Okay, so if I can make just a comment. Yep. I was looking at some of this magnetite, early magnetite alteration bearing, and in my mind passed like this early magnetite array is nothing else than a trap, exactly the same way that it acts as structure. It's everywhere, And probably some of the people here exploring, they drill probably 100 or 2,000, I don't know how many magnetite targets, and only very few of them turned as mineralized. So if you really look across the Mount Isa, and magnetite is just another possible trap along a structure. So that's all. Thank you.
Yep, and just a quick comment with the statistical band. Even though intuitively we know that magnetite is the most common mineral in and close to ore, but the iron content doesn't co-vary with copper, so it doesn't end up there. So which gives another indication that copper is separate. And in places it's quite clear that in places like Stara, well, most of that magnetite doesn't have anything to do with anything. It's just a host rock.
We have one question online.
Could I just answer Johan's question too,
sure.
or just give if Jim Austin were here, he would say that the actual ore zone in the work that they did, he said this quite often, that the ore zone in comparison to the surrounding magnetite body is actually has a drop in magnetic susceptibility, so that the actual ore zone is, that a lot of the magnetite there is pre-existing magnetite that's being then converted to hematite at the time of mineralization, though obviously there's not an enormous amount of hematite, but he makes that point quite a lot.
And online, Anthony Burnham has asked, can you comment what the distribution of orthoclase versus microcline implies for the thermal conditions during mineralization?
Very quick answer to this very interesting question. But for now, we focused very firmly on stating facts instead of figuring out how it works. So we made a very deliberate effort. Let's just sort out facts first and finish the story later. And that's exactly where I want to finish it. And lots of the data, even geochemical data, came from Web3, not final reports. So until we get all our information straightened, I wouldn't want to go into interpretations.
And Paul?
Yeah, Vladimir, so some of these deposits have a typical IOCG signature, and a lot of them don't.
Yes.
And with a lot of them, you don't have a clear mineralogy that is distinct from the surrounding rocks. Is that correct? Or do you still see a very distinct gradation into the deposit?
Mostly we do see clear mineralogical and geochemical signals. Like most of the geochemical classification was done on ore samples. So it's pretty much, it's all dominated by the ore signals. And there are quite typical, quite clear mineralogical combinations of proximal alteration, whether it's an assembly-like geochemistry or not.
So the reason why I'm asking, at Tig Hill, we are looking at fluid inclusions. And at first, we took all our samples from within the deposit. And then we thought, shit, we are completely biasing ourselves by just looking at the alteration directly at the deposit. We should actually step outwards and look at the regional signature and compare it. And the fluid inclusion signature regionally is identical, and the alteration is sort of identical to what we get proximal. Not entirely, there's differences, but there's a lot of similarities. And I'm just wondering, how do you differentiate a mineralizing fluid from a regional fluid flux? And how do you know for sure that what you are sampling is a reflection of the mineralizing fluid coming through and not just some dispersion of a pre-existing enrichment by a regional fluid flux?
In places like in the vicinity of Ernest Henry, we do have a very serious coverage going kilometers away. And we do have very clear spatial relationships of some minerals with mineralization, and in places we can clearly see a combination of certain mineralogy and geochemistry suggestive of fluids which is proximal or ore-like. So, for example, we do know that there is actinolite which is regional, and we do have very strong modern enough evidence to say that lots of actinolites came as part of mineralizing event. So actinolite integron with chalcopyrite, it's pretty clear evidence. So it's what makes it complicated. Just about every mineral which is considered typical for proximal alteration also occurs elsewhere as a normal regional alteration rock. Yes.